Hello, students. We're going to be doing, stop. Hello, students. Stop. Got a smile. Hello, students. We're going to be going on to the next topic, work and energy. And so today, this first video is going to be about the idea of work. So I want to show you something here. I'm going to tilt this this thing down so you can see I've got a little car here, and obviously I can make the car go. It's one of these electric cars, but let me just show you for the purpose of this demo what I need to. So here we go. When I apply a force, that's my finger here, is applying a force, and the force makes the object move, then that is called work. All right, so one more time. I'm doing work as I do that. All right, now the amount of work is given by the formula, here we go, work, which gets the letter W, is equal to the push, the force, times the distance. Now, we're going to have to be a little careful here. I know I wrote here distance, but the direction is going to matter. So D could just as well mean displacement, and so distance, displacement. So we're going to have to be a little careful about our wording pretty soon. So yeah. Now this formula here is fine for calculating work as long as the force is not changing, right? I was pushing with equal, I didn't go from 1 to 2 to 1 newtons. And also, when the force is in the same direction as the motion. So you see the direction's coming up already. Now let's continue here. The units for work are going to be newtons, right? That's the push, times meters. And that's the displacement or distance that you pushed it. And the Newton times meters, that's equivalent to a new unit, which we're going to call the joule. So Newton meters or joules is the same thing as these basic units. So kilogram meters squared over second squared is equivalent to joules, equivalent to Newton meters. And that's because if you go back a ways, force is mass times acceleration. So mass is kilograms, acceleration is meters per second squared. So newtons are kilogram meters per second squared. And now the unit of work, the newton times the meter, is equal to kilogram meters per second squared times meters. And so we get this. And so yeah, here we are. We've got that kilogram meters per second squared is the same thing as joules. All right, so let's move on here. So, okay, let's have some examples with some numbers, really simple examples. I've got a bulldozer is pushing a mound of sand, and the push is 20,000 newtons, and the bulldozer pushes the sand 15 meters. How much work did it do? So it's force times distance or displacement, and you multiply, you get 30,000 Newton meters or 30,000 joules. Okay, so that's one example. Let's have another example. Tarzan lifts up Jane, and Jane weighs 600 newtons. All right, so he's lifting upward, right? So the motion is upward, the force is also upward, and to put her on the elephant. Okay, fine. How much work did he do? So here's the force, 600 newtons. The displacement, change in position, right, is 1.5 meters. You multiply and you get your answer, 900 joules. So down here, I drew diagrams because I want to kind of emphasize the direction aspect of this here. The bulldozer was pushing in the positive direction. The displacement was positive. The work was positive. In the case of Tarzan, he had to go and lift, his hand was pushing upward while he was lifting, and the displacement was upward. And so, yeah, they're in the same direction, and the work was positive. But if the work and the displacement are not in the same direction, then things get a little bit more difficult. So here you notice I've started putting vector signs here over the force and over the displacement, because now we're really paying attention to the direction. This formula here, it has the magnitude of the force and the magnitude of the displacement, and we're multiplying by the angle between the two vectors. So theta is the angle between those two vectors. So let's have an example so you can understand what I'm talking about. So here in my example, Peter is pulling Jeff. And Peter's pull, the pulling force is at 30 degrees above the horizontal. So that's what I'm showing here. And the displacement was 8 meters. And okay, so how much work did Peter do? I kind of wish maybe I should just, here, let's make a temporary correction here. Let's write here displacement, because displacement has direction in it. I like that better. Okay, so the displacement vector is to the right. The force in this vector is up and to the right at an angle of 30 degrees. And so now you can put in your numbers. The magnitude of the force is 100 meters. The magnitude of the displacement was 8 meters. The angle was 30 degrees. And you get your answer. After taking the cosine and multiplying, you get 693 joules. All right. So, now, I've got a little question going here. Yeah. What if I ask you the question, how much work did gravity do? So what would you do? The force of gravity is downward, right? And the angle would be 90 degrees, right? And what's the cosine of 90 degrees? If you said 0, yeah, you are right. And so what we find out is that the work that gravity did, which was downward, was 0 joules of work. And so this is a very important general rule. This is going to come up here and there. When the force and the displacement directions are perpendicular, then no work is done by that force. Okay. All right, so yeah. Okay, now here's another example. So I've got a parachute lowering 1 ton of emergency food. So a ton is 1,000 kilograms, but you knew that. And yeah, the flood victims below need that food. How much work did the parachute do? So when you think about this, all right, which way is the parachute pulling or pushing on this box of stuff? Well, it's preventing the box from falling too fast, right? It does that by exerting a upward force. By the way, that bong that you just heard is a clock from Japan. Did you know that physicists are a little bit nutty, crazy about clocks and other gadgets? So that's me. I like clocks. Anyhow, the force, it was upward, and the displacement was downward. And so, if you draw it this way, you can see that the angle between the force vector and displacement vector, and oh my God, I'm going to lose points here. I need to have vector signs here, is 180 degrees. And the angle, okay, well, the cosine of 180 degrees is -1. So you have the force, the displacement, times -1, you multiply, and you get the answer. Negative 4,900,000 joules. So the work that the parachute did is negative. And this happens whenever the force and displacement are in opposite directions, or when the angle between the force vector and the displacement vector is more than 90 degrees. This formula here, f d cosine theta, where f is the magnitude of the vector and d is the magnitude of the displacement. And there's a special notation for this. It's called the vector dot product, and it gets written the vector, big fat dot, another vector, and so when you see that, it's called the vector dot product, and this is what it means. Oops, sorry about that. Okay, so we could write that the work is the force vector dotted with the displacement vector. Okay, and finally, let's have another little question here. How much work does gravity do in this example, right? So think about it. Let's see if we can figure this out. I'll use this space here to draw. We have the displacement vector. It's still downward, right? So this is still my displacement vector. And my gravity vector is downward, right? So here it is, FG. And so the angle here, I didn't do a good drawing here, but the angle is 0. And the cosine of 0 is 1. And so it's going to be 9,800 times 500 times 1. And so the work done by gravity will be positive 4,900,000 joules. And so the answer is that it's plus positive 4,900,000 joules there. Okay, and I've got one more thing that I'm going to show you. It has to do with the car. Okay, so hopefully you can see this. The car wants to go, and you see it's pushing against my finger. So if I have this situation here, right, the car wants to go, but my finger is pushing the other way. It prevents it from going. My question to you is, what kind of work was my finger doing? Was it positive work or negative work? Okay, I think we should stop here. Thank you.